Welcome back to Mechanical Engineering Made Simple.
Hey, glad to be back at the workbench.
Yeah, so right now, inside the device you're using to listen to this, there is this miniature high-speed storm taking place.
Oh, absolutely. It's wild to think about.
Right, like liquid is boiling, it's turning into vapor, traveling at incredible speeds, and then raining back down. And all of this is happening in absolute silence with zero moving parts.
Yeah, no mechanical pumps at all.
Exactly. So today we are taking a deep dive into a piece of technology that, I mean, it feels almost like magic the first time you learned about it. We're talking about the heat pipe.
It really is one of the most elegant solutions in modern engineering.
For sure.
You can really consider this deep dive a sort of classroom walkthrough of the phase change physics that, keep our modern world running.
Because without them, our tech would basically melt, right?
Pretty much. We're drawing from a really dense engineering text today to explore how we manage extreme temperatures. And doing it in everything from the laptop sitting on your desk to a satellite floating out in the vacuum of deep space.
So for you listening, our mission today is stripping away all the complexity. We want to look at the pure causality of how these things actually work.
Yeah, we have to get down to the basics.
Like, how do you move astronomical amounts of heat using nothing but capillary action and fluid dynamics?
Right. Well, to understand that, we have to start with the fundamental anatomy of a conventional heat pipe.
Okay, set the scene for us.
Picture a completely sealed, hollow metal container. It's usually just a tube. Inside that tube, lining the inner wall, is this porous wick structure.
Got it. A hollow tube lined with a wick.
Yep. And soaked into that wick is a small amount of working fluid. We basically divide the simple setup into 3 functional zones.
3 zones. Okay, what are they?
You've got the evaporator at one end, the condenser at the other end, and the adiabatic or transport section right in the middle.
Okay, let's unpack the mechanics of that. So heat hits the evaporator section.
Yeah.
The liquid in the wick absorbs that heat and turns into vapor.
Exactly.
And this is the critical trick here, isn't it?
Yeah.
It's not just warming up the liquid, it's actively forcing a phase change.
That is the ultimate cheat code of thermal management, honestly.
How so?
Well, when you simply heat up a solid piece of copper, you are using sensible heat. The copper just gets hotter.
Right, conduction.
But when you boil a fluid, you are dealing with the latent heat of vaporization. It takes a massive amount of energy to force those liquid molecules to break apart and become a gas.
Because you're changing the state of matter.
Precisely. By vaporizing the fluid, the heat pipe absorbed orders of magnitude more energy than solid conduction ever could.
The source mentions some crazy numbers for this, right?
Oh, yeah. We are talking about energy transport capabilities reaching 10 to the 8th power watts per square meter in high-end applications.
10 to the 8th power. That is just an insane amount of energy packed into a fast-moving gas.
It really is. So the fluid vaporizes, absorbs all that heat, and that creates a high-pressure zone.
And naturally, that hot vapor shoots down the hollow center of the plate, the transport section, just trying to escape the pressure, right?
You've got it. It hits the condenser end, which is cooler, so it condenses back into a liquid and releases all that stored heat into a heat sink.
Okay, but here is the brilliant part, and I guess the core engineering challenge. You now have all your liquid sitting at the cold condenser end.
Right, it's stuck at the wrong end.
Yeah, you need it back at the hot evaporator end to keep the cooling cycle going. But, and this is the kicker, you have no pump.
0 moving parts.
So this is where that porous wick structure lining the wall becomes the engine of the entire system, right?
Exactly. It's all about the wick.
I always try to visualize this for our listeners. Is it basically like a paper towel soaking up a spill on your kitchen counter, but trapped in an endless high-speed vacuum loop?
That's a really great way to picture it, actually. But let's take that paper towel and put it under a microscopic lens so we can really see the physics.
Okay, let's zoom in.
As the liquid vaporizes in the hot evaporator, the surface of the liquid inside the tiny pores of the wick, what we call the meniscus, recedes.
It kind of dips down.
Right, it curves inward, deeper into the wick. Meanwhile, down at the cold condenser, vapor is constantly turning back into liquid.
It's filling those pores up.
Exactly, making the meniscus down there bulge outward.
Okay, so you have this receding concave curve of liquid on one side and a bulging advancing curve on the other.
And that difference is everything. Engineers use the Young-Laplace equation to describe what happens next.
Oh, right. Surface tension.
Yeah. Because water molecules love to stick together through surface tension, those deeply curved liquid surfaces in the hot end act like microscopic trampolines.
Trying to snap back flat.
Exactly. That tension creates a negative pressure. It's basically suction. This difference in the radii of curvature between the two ends creates a literal capillary pressure gradient.
Wow. So the wick uses this gradient to pull the liquid from the cold end all the way back to the hot end.
Yep. As long as that pulling force is stronger than the friction of the fluid moving through the wick, the loop just runs infinitely.
It's a beautifully closed loop. But, I mean, a basic paper towel and water setup isn't going to cool a nuclear reactor.
No, definitely not.
And it's definitely not going to work on a spacecraft. We have to engineer the guts of these pipes specifically for the thermal environment they live in, don't we?
We absolutely do. And the first major choice an engineer makes is the working fluid itself.
Because of the temperature ranges.
Right. You have to match the fluid to the temperature zone. Because if the environment is too cold, your fluid stays completely frozen and the pipe is useless.
It's just a frozen stick.
And if it's too hot, the fluid turns entirely into a gas, the pressure maxes out, and you lose the capillary liquid loop entirely. So we categorize them into 4 distinct temperature zones.
Okay, walk us through those environments. Let's start with the extreme cold.
First, we have cryogenic heat pipes. These operate way down from 1 to 200 Kelvin.
So water's out of the question.
Oh yeah, water would just be a block of ice. So you are forced to use fluids like liquid nitrogen, oxygen, or even helium.
Okay, then step it up to normal conditions. What does that look like?
That's the room or low temperature category. That operates between 200 and 550 Kelvin.
And what fluids go in there?
This is where you find water, ammonia, and methanol. This is the zone for your laptop, your gaming console, basic terrestrial electronics.
Makes sense.
Next up are the medium temperature heat pipes from 550 to 700 Kelvin. Those utilize fluids like mercury or sulfur.
Which sounds intense, but what happens when things get insanely hot?
Above 700 Kelvin, we enter the high temperature zone. For these extreme industrial or aerospace environments, water or ammonia would instantly flash into useless, highly pressurized gas.
Right, they just blow up.
Exactly. So engineers use liquid metals. We're talking potassium, sodium, or even liquid silver.
Wait, I have to stop you there. If the working fluid inside the pipe is silver or sodium, it's essentially just a solid brick of metal at room temperature.
It is.
How do you even turn that on?
Yeah.
It has to awkwardly thaw itself out before it can do its job. It's kind of like me before my first cup of coffee.
It's a very chaotic morning routine for a heat pipe, yes.
I'll bet.
You're hitting on a major engineering hurdle, which is called the startup transient phase. You can't just apply heat to a solid chunk of sodium and expect this elegant capillary flow to instantly start.
Because it's solid.
Right. First, the intense heat has to transfer through the pipe wall and into the solid metal entirely via conduction.
And conduction is slow. It's just atom by atom bumping, transferring heat physically rather than moving it quickly through a fluid.
Exactly. It's a brute force physical battle at first. The heat has to slowly melt the solid metal that's trapped inside the wick structure.
Ah, right, because it froze inside the pores.
Yes. Only after a section becomes liquid can it even begin to vaporize. And then the vapor pressure is so weak at first it struggles to travel down the pipe.
It sounds like a total bottleneck.
It is. It's a highly complex transition where the metal slowly wakes up, melts, vaporizes, and finally builds enough pressure to establish that endless loop.
That's wild to think about.
Yeah.
And I imagine the wick structure itself has to be custom tailored for these different fluids, too. You can't just use a standard wire mesh for everything, right?
You definitely can't, because wick design actually has a fundamental physical conflict built into it.
A conflict? Like what?
Well, to get a massive capillary pulling force, that suction we talked about earlier, you want extremely tiny, fine pores.
Right, tighter curves mean more suction.
But tiny pores create incredibly high flow resistance. It's like trying to drink a really thick milkshake through a microscopic cocktail straw.
Oh, man. So you want tiny pores for strong pulling power, but wide open pores for fast flow. How do you solve a paradox like that?
By abandoning simple, uniform materials, what we call homogeneous wicks, and instead we engineer composite wicks.
Okay, so mixing them up.
Yeah. A homogeneous wick is just one uniform structure, like a tightly wrapped wire screen or sintered metal powder. It does one job well, but usually fails at the other.
And a composite wick.
A composite wick splits the jobs up.
Give me a real-world example of what that looks like inside the pipe.
Okay. Picture a screen-covered, grooved wick. Engineers will cut wide, open channels grooves lengthwise down the solid metal wall of the pipe.
Like little gutters.
Exactly. Then they lay a very fine metallic screen right over the top of those grooves.
Oh, I see.
So the fine screen right at the surface handles the vaporization and generates massive capillary pulling pressure.
But the liquid doesn't travel through the screen.
Right. Once the liquid is pulled in, it drops down into those wide open grooves to actually travel back to the hot end.
That's brilliant. It's like having a high-powered pump pulling the water, but feeding it through a massive smooth fire hose instead of tiny straw.
You completely optimize for both pressure and speed. But even with brilliant wick design, every engineered machine has a breaking point.
Sure, nothing is infinite.
And that brings us to the operational boundaries. Heat pipes do fail, and they fail in very specific, mathematically predictable ways depending on how you push them.
So let's talk about what happens when this magic trick stalls out. The source broke these down into catastrophic limits, where the pipe actually stops working, and performance limits, where just bottlenecks.
That's right.
Let's look at the catastrophic ones first, where the evaporator wick just dries out completely.
Okay, the most common failure is the capillary limit. This happens when you simply ask the wick's microscopic trampoline effect to do too much.
It just can't keep up.
Exactly. The total pressure drop inside the pipe, which includes the friction of the liquid moving through the wick, the friction of the vapor moving down the center, and fighting gravity if the pipe is tilted upward, it all just overcomes the maximum capillary pumping pressure.
The pump just stalls. The liquid can't get back fast enough, the hot end boils dry, and the pipe completely stops transferring heat.
You've got it. And if you push the raw heat too hard, you hit a different one. The boiling limit.
That sounds violent.
It is a violent failure. Normally, you want the fluid to evaporate cleanly right at the surface of the wick, but if the radial heat hitting the pipe is too intense, it causes the liquid to violently boil deep inside the tiny pores of the wick itself.
Oh, like when a pot of water gets way too hot and starts forming big rolling bubbles at the very bottom, under the water.
Exactly like that. We call this nucleate boiling. When those vapor bubbles form deep inside the microscopic pores of the wick, they get trapped there.
They can't escape.
Right, they act like physical roadblocks, completely blocking the incoming liquid from reaching the heat source.
So the hot spot gets starved of liquid, and again, you hit dry out.
Yep.
Okay, so capillary limit is a stalled pump. Boiling limit is a blocked road. Is there a third way to break it?
Yes, and I think it's the most fascinating one, the entrainment limit.
Entrainment, what's happening there?
Remember, inside this pipe, you have liquid flowing quietly in one direction through the outer wick, while at the same time, a massive storm of vapor is blasting in the exact opposite direction down the hollow center.
All right, they're passing right by each other.
If you demand too much heat transfer, that vapor velocity becomes extreme.
Oh, I can see where this is going. It's like wind blowing a waterfall backward.
That is exactly the mechanism. The sheer force of that high-speed vapor physically rips liquid droplets right off the surface of the wick and carries them backward to the cold end.
It just strips the wick dry.
Yeah. Engineers actually calculate a value called the Weber number to predict this. The Weber number is essentially a mathematical tug-of-war.
Between what?
Between the sheer ripping force of the high-speed vapor and the stickiness of the liquid's surface tension trying to hold itself together on the wick.
And if the vapor wins the tug of war, the liquid is torn away, the hot end starves, and the pipe fails.
Exactly.
Okay, those are the catastrophic limits. What about the non-failures? The limits that just throttle the system and ruin its efficiency?
Well, the first throttle is the viscous limit. This usually happens during cold startups.
Like the solid sodium we talked about.
Right. When the temperature of the system is extremely low, the vapor pressure is correspondingly low. It's so weak that it struggles to overcome its own viscous friction.
So the vapor is incredibly sluggish.
Yeah, it's like trying to sprint through a ball pit. The vapor is just fighting its own thickness. You really just have to wait for the temperature to rise enough to build the pressure.
Makes sense. What's the other one?
The other non-failure limit is much more dramatic. It's the sonic limit.
Sonic. Wait, as in Mach 1, the speed of sound?
Yes.
Really? Inside tiny copper tube?
Absolutely. At low vapor densities, when the pipe is trying to move a massive amount of heat very quickly, the vapor has to accelerate.
Okay.
Eventually, the vapor hits the speed of sound right at the exit of the evaporator section.
That's unbelievable.
When a compressible gas hits Mach 1, the flow becomes what we call choked. It behaves exactly like a converging, diverging nozzle on a rocket engine.
So it hits a literal speed limit. It forms a thermal traffic jam right at the speed of sound.
You cannot force more mass flow through that pipe once it chokes, no matter how hard you try.
I want to make sure you, the listener, grasp the consequence of this. If you hit the sonic limit and you try to force more heat out of the cold end, say, by blowing a bigger fan over the condenser, it won't cool the hot end any faster.
Not at all. Pushing more cooling at the condenser end won't lower the evaporator temperature one bit once the flow is choked.
Because the vapor is physically maxed out.
Right. It just drops the temperature at the condenser, which creates a massive temperature difference along the pipe.
And that defeats the whole purpose.
Exactly. The entire beauty of a heat pipe is that it maintains a uniform, flat temperature from end to end. The sonic limit destroys that completely.
So we have all these strict limits. Friction, boiling, sonic, traffic jams. But technology hasn't slowed down.
Not at all.
I mean, the heat density of modern microchips or large-scale space stations is off the charts. How did engineers design around these fundamental physics problems?
Well, when traditional wicks became the bottleneck, engineers simply reinvented the geometry.
How so?
The first major evolution was the microheat pipe. It was developed specifically to eliminate microscopic hotspots on silicon wafers.
How small are we talking here?
The internal channels are microscopic, roughly 30 to 1,000 micrometers wide.
Wow.
And the genius of a microheat pipe is that it has no traditional wick at all. No screen, no metal powder.
Wait, how do you get capillary pumping without a wick?
By using the geometry of the pipe itself, instead of round tubes, they use non-circular channels, like tiny triangles or squares.
Oh, because of the corners.
Exactly. Because of surface tension, liquid naturally wants to pull itself into tight, sharp corners. Those microscopic sharp corners act as the liquid arteries.
That's wild.
The vapor rushes down the open center of the triangle, and the liquid crawls back silently along the sharp corners.
That is unbelievably elegant. You just use the shape of the container to pull the fluid.
It is. But if you need to move a lot of heat and you still want to avoid the friction limits of a wick, you move to something called a pulsating heat pipe, or PHP.
Pulsating? What does that look like?
Imagine a single, continuous, highly flexible capillary tube. You bend it back and forth into a zigzagging, serpentine shape that weaves between the hot processor and the cold fan.
Okay, a zigzagging tube with no wick. Why is it called pulsating?
Because the tube diameter is so small, the fluid inside naturally separates into alternating slugs of liquid and bubbles of vapor.
Like an air bubble in a syringe.
Exactly. When heat hits one end, the vapor bubbles expand rapidly. This physically pushes the liquid slugs toward the cold end.
Oh, I see.
Then at the cold end, the vapor condenses, the pressure drops, and it creates a suction that pulls the liquid back.
So it's just this violent interplay of boiling, pushing, and condensing, pulling.
Yes, it causes these alternating slugs of liquid and vapor to violently oscillate back and forth.
That sounds chaotic.
It's like an off-balance washing machine of thermal transfer. It utilizes both sensible and latent heat, and because it has no wick, it completely bypasses the traditional capillary limits we talked about.
Okay, that handles high-heat terrestrial stuff.
But
But what about the truly massive applications, like space stations we mentioned?
for large-scale aerospace, we rely on the ultimate evolution of the technology: capillary pumped loops, or CPLs, and loop heat pipes.
Loops? Okay, how do those differ?
Think back to the entrainment limit, the wind blowing the waterfall backwards.
Right, because they're sharing a crowded two-way street.
Exactly. To solve that, loop heat pipes separate the vapor and the liquid into completely different smooth-walled tubes.
No, they don't touch at all.
Nope. They strip the wick out of the entire transport section.
Wait, if there's no wick in the transport tubes, where's the pump? How does the liquid get back?
The wick is engineered only inside the evaporator.
Oh, okay.
Heat hits the evaporator, vaporizes the fluid, and the vapor shoots down a dedicated, smooth-walled pipe to the condenser. It turns back into liquid and then travels through a separate, dedicated, smooth pipe back to the evaporator wick.
So you completely turn the crowded two-way street into a highly efficient one-way thermal highway.
And because those smooth return pipes have almost zero flow resistance, you can transport heat over massive distances, meters or even tens of meters.
Which is obviously non-negotiable for a large spacecraft.
Exactly.
But let me challenge that for a second. If the wick is only located at the hot end, what happens if things flip?
What do you mean?
Say the condenser suddenly gets hotter than the evaporator. Does the loop run in reverse and accidentally pump heat the wrong way?
It doesn't, and that quirk of physics is actually its greatest feature.
Really?
Yeah, because there is no wick in the condenser to provide that capillary suction, if the temperature's reverse, the loop simply shuts down. The fluid stalls, It acts as a thermal diode.
Thermal diode, like a
Uh,
one-way valve for heat.
Precisely. Imagine a highly sensitive, freezing cold infrared telescope on a satellite. The loop heat pipe is pulling the electronics heat away and radiating it out into the dark of space.
Huh?
But suddenly, as the satellite orbits, that radiator panel rotates and faces the blistering heat of the sun.
Oh, man. If it was a normal copper rod, it would channel all that solar heat straight back into the delicate telescope and just instantly fry it.
But because a capillary pump loop is a thermal diode, the moment that space radiator gets hotter than the telescope, the fluid flow stalls. It actively blocks the heat from coming inside.
Wow.
It's not just a cooling loop, it is an active thermal shield.
We've really gone from a paper towel soaking up water on a counter to an engineered thermal diode defending spacecraft from the sun. The sheer scale of what you can do with phase change is incredible.
It really is. But I want to leave you, the listener, with a final thought to mull over, something that stretches beyond the laptops and satellites we've talked about today.
Let's hear it.
Next time you look up at the moon and think about the permanent lunar bases humanity is currently designing, ask yourself, how do you survive there?
The temperature swings are insane.
A lunar day swings from 250 degrees Fahrenheit in the blistering sun down to negative 200 degrees in the dark. You're in a complete vacuum with barely any gravity to help move your fluids around.
So normal tech won't work.
Traditional pumps and radiators will freeze, burst, or just stall out. The answer to keeping human beings alive in that extreme environment is sitting right in the wickless phase change physics we just explored today.
Victory belongs to those who refuse to lose. Thanks for riding with me, Design Junkies. Stay hungry. If this episode gave you even one solid takeaway, drop a comment. Takes you a few seconds, but it tells me this workbench is actually helping and worth keeping alive. We don't make a dime off this, and that's by design. As long as it's helping you get sharper, that's enough.